Okay, good day to each and every one of you. This will be another sample problem for axial stresses. So for this example, I have here a three-part segmented structure with their own respective parameters. For the steel, we have the cross-sectional area equivalent to 500 square millimeters and a maximum allowable stress equivalent to 120 megapascals. And for the timber, we have a cross-sectional area of 2,000 square millimeters and a maximum allowable stress equivalent to 12 megapascals. And for the concrete, we have 8,000 square millimeters of a cross-sectional area and a maximum allowable stress equivalent to 16 megapascals. And the problem wants us to solve P sub max. Okay, the maximum allowable load that we can apply to our structure so that it wouldn't get destroyed. So for us to solve for P sub max, we need to sectionize our structure into three segments because we have three different materials, that's number one, and their cross-sectional area is varying. Means to say they don't have the same cross-sectional area. They have difference because this one is 500, this one is 2000, and this one is 8000. And for every material, they have their own inherent properties like strength, toughness, durability, malleability, ductility, stiffness, and many more. Those are some material properties. So that's why it's really important for us to consider the fact that they have different materials. Means to say they have different inherent properties. For example, this one is timber, and this one is concrete, and this one is steel. Obviously, if we look at here in our free body diagram that the first one to give in would be the timber because this is made up of wood. And this one is steel, which is harder and has a lot of more strength. And for this one is concrete, which is much stiffer. So obviously, if we're going to use just simple deduction that the first one to give in, if we are going to apply a force downward in the vertical axis, would be the timber because this is much more fragile compared to steel and for the concrete. So that's why it's really important for us to know what would be P sub max or the maximum allowable load that we can impose on our structure so that everything would still settle as one piece. Okay. So for us to solve this one, we're going to section our structure into three segments for the steel, the timber, and the concrete. And we're just going to apply the summation of forces along the vertical axis, and then basically that's it because this is just a simple structure and all of the forces are going down. So we're not going to use any summation of moments for this problem. So let's start by solving first for the steel section. Okay, we're going to cut it here at this portion of the structure. So always you just need to construct the free body diagram before solving so that you can deduct all of the forces, be it external and internal, of this structure. So this one is the cut section. For this problem, we have 2p going at the vertical axis downward. So this one is 2p, and according to the laws of equilibrium, there should be a counteracting force, this 2p. So if 2p is going downward, then obviously this one should be going up in order to counteract 2p. So this one is for the steel, so let's say that is P sub st. So applying the summation of forces along the vertical axis, so that should be plus going up. Depends on you if going down is positive and the other way around is negative. So that depends on you, where you are convenient. Summation of forces along the y is equals to 0. So 2p, so that would be negative 2p plus P sub st, and then transposing P sub st, that is so simple, is equals to 2p. So this one is equation number 1. So that's straightforward. And then let's proceed to the timber section. So we're going to cut it here, and then we're going to consider everything that is on top. So if this is the 2p, no, this is 2p, then this is the timber section where we cut the structure. So if we go back to our free body diagram, we have here a force P going up this portion. So that should be P going up, And based on our free body diagram, two p's going down and then a single p going up. So obviously we are going to assume that this portion is also going up because 2p is much greater compared to p. So obviously we're going to need another force going up in order to counteract this 2p. So this one is p sub t for timber. Then applying the equilibrium, summation of forces along the y-axis is going up is positive. So that should be p sub t for timber, and then we have plus p minus 2p. And then isolating p sub t that should be positive 2p minus p because you're just going to transpose this one to the other side and then rearranging. So p sub t now is equivalent to simply p. Okay. And after doing that, that should be equation number 2. This one is equation number 2. Then let's proceed to the concrete section, which is this one. So we managed to section our concrete at this portion, so we don't know what is the equivalent length. So for now, we don't need the length. So we're going to consider everything that is on top because we are sectioning. So by doing that, this one is the steel, this one is for the timber, and this one is for the concrete. Going like this. So this one it has 2p, this one it has p, and then let's go back to our free body diagram. In between the timber and the concrete, it has 4p going downward. So it should be here. So this one is for p. So this one is the portion we managed to cut the concrete section. So 4p is going down and then 2p is going down, and then we have a single p going up. So obviously we're going to counteract these forces, 2p and 4p, going upward in order to stabilize everything. So this should be p sub c, corresponding to the internal force at the concrete section. So summating all of those forces along the vertical axis. So going up is positive, summation of forces along y is 0. So p sub c minus 4p plus single p and then minus 2p. Then isolating p sub c. So p sub c now is equivalent to 4p and then plus 2p minus p. And then let's substitute it here. P sub c is simply 4 plus 2p is 6p minus p is 5p. So that should be equation number 3. So we managed to solve 1, 2, and equation number 3. And the next one is to simply apply the average stress formula. So don't forget for this 3, just going to clear up some space in order for us to solve. Okay, so the average stress formula is basically sigma is equals to the applied force over the cross-sectional area. That's our working formula for this problem. So let's start again with let's start at the steel section. Okay. For the steel, the cross-sectional area is 500 square millimeters and the allowable maximum stress is 120 megapascals. So let's use the working formula. So sigma sub st for steel is equals to p sub st divided by a sub st. We just need to solve for this one, p sub st, and then we all know that the equivalent of p sub st is equals to, so but p sub st is equivalent to, based on our solution just recently, is equals to 2p. So solving for p sub st, so sigma sub st is equivalent to 2p over a sub st, and then solving for p is equals to sigma sub st multiplied by the area sub st divided by 2. So solving for that one, p is equals to Sigma sub ST is equivalent to 120 megapascals based on the givens. 120 megapascals multiplied by the cross-sectional area equivalent to 500 square millimeters. But if we're going to convert that into square meters, we need to do it like this. So 500 square millimeters multiplied by 1 meter for every 1000 millimeters, and then squared because we're talking about the area. Okay, so square millimeters, cancel. The only remaining unit for this one is simply distributing that one here, simple algebra, so it becomes squared. So solving for this one, P, let's go here, going up, P is equals to 30,000 newtons. So P for the steel, okay, let's just simply assume this for the steel is 30,000 newtons. So this one is for the steel. It can handle up to 30,000 newtons worth of axial force. And let's proceed to the remaining two. I'm just going to border around this one. Let's go for the timber. Okay, so sigma sub t is equals to P sub t divided by A sub t, solving for P sub t. So based on our solution just recently in the summation of forces, P sub t is equals to single P. Okay, so going to substitute that here, solving for P sub t. So P is equals to sigma sub t multiplied by the cross-sectional area, and then just substitute. P is equals to the maximum allowable stress is 12 megapascals. So 12 megapascals multiplied by the cross-sectional area equivalent to 2000 square millimeters. Then conversion factor for every 1 meter it has 1000 millimeters, and then squared. So P, the maximum load for the timber is approximately equivalent to 24,000 newtons. So this one is 24,000 newtons for the timber. And the remaining one is solving for basically for the concrete. I hope you don't forget that. The first one is 30,000 newton for the steel, then 24,000 newtons for the timber, and then the next one would be for the concrete. I'm going to free up some space here in order for us to solve the remaining parameters for the concrete section. Okay. So sigma sub c is equals to P sub c over A sub c, solving for P sub c, but based on our solution just recently, P sub c is equivalent to that should be 5p. So that should be 5p. Then solving for this one, so sigma sub c is equals to 5p over A sub c, solving for p, that should be p is equals to sigma c A sub c over 5. So let's go here. P is equals to the maximum allowable stress equivalent to 16 megapascals. So that should be 16 megapascals multiplied by the cross-sectional area equivalent to 8,000 square millimeters. So 8,000 square millimeters, 1 meter for every 1,000 millimeters, and then squared, then solving, divided by 5, then solving for P, that should be for the concrete equivalent to that should be 25,600 newtons. 25,600 newtons for the concrete. And based on our previous answers for the timber, that was 24,000 if I'm not wrong. So that should be 24,000 newtons. And for the steel, P sub ST is equivalent to 30,000 newtons. So the question here is, what would be P sub max? So based on these three axial forces that we have, the maximum allowable load that can be applied on our structure is obviously this one. Okay, because the answer for that is, if we are going to use again this working formula, no, and don't forget that this timber has a maximum allowable stress equivalent to sigma sub t is equals to 12 megapascals. Okay, don't forget about that. If we're going to use this formula and then input, let's say for example 30,000 newtons to this portion, and changing the value for the sigma for the timber, it would exceed 12 megapascals. Okay, because this is the allowable stress, working stress for the timber. If you're going to input 30,000 to this portion with the same cross-sectional area for the timber, obviously the answer for this sigma would exceed 12 megapascal. So that's why, so that's the reason why we need to settle for the least valued number for our answer. So that should be 24,000 newtons. For example, if you're going to apply 25,600 newtons to this P here, retaining the cross-sectional area of the timber, so you would get a different answer for sigma, which exceeds again 12 megapascals. Okay, so that's why P sub max is this one, 24,000 newtons. So that's the answer for this problem.